Hi guys, welcome back to another video of me teaching, and today I have the 18th IMO 1976 question 6. So why don't we just get into question? Well, this question looks so complicated, right? We have the floor function and we have some bunch of stuff. Well, actually, it is not that hard. So let's first read the question. We have a sequence that is defined by u0 to be this, u1 to be that, and we also have a formula for un plus 1 using the previous two terms. And we want to prove that the floor function of the general form un is equal to this whole thing. So, like I said, if you've watched some of my previous videos, then you know we only have two terms. And we want to find already the general form using just two terms. Well, that's quite impossible, right? It might not be impossible, it might just be really hard. But to make it ideal, we want to know some more terms. For example, what about u2? Well, lucky for us, there is a formula that does it for us. So u2 is equal to the one before, u1, multiplied by u0 squared minus 2 and then minus u1. So if we expand this and plug everything in, we get u1 is 5 over 2, u0 squared is 4 minus 2 is 2, so times 2, and minus 5 over 2. So this is just 5 over 2. And also we can figure out what u3 is. But I won't be doing that in this video because it will take quite a lot of time. I'll just tell you that u3 is 65 over 8. Okay, so now we already have four terms, but we still can't really see a pattern, right, in the fractions. So if we can't see a pattern in the fractions, then usually we want to partial. So for example, we can split u0 into 1 and 1 over 1. u1 can be split as 2 and 1/2. u2 is also 2 and 1/2. And u3 is 8 plus 1 over 8. And for fun, you can check out u4, which is 32 plus 1 over 32. So now we see there is a pretty clear form of un. So our guess is that un is xn. So basically xn is just something, and we add 1 over that same something. So this is our guess. And also a second guess is that xn we think is probably equal to some power of 2. Because look, 2, 8, 32, all powers of 2. So it might be 2 to the power of something, an. So how can we verify that this guess is true? Well, we already have one given information. This. So if we plug it into that and we manipulate it a bit, then we can see if this guess is true. So I'm going to rub this out. But before we do any of this plugging in, for these further steps, we usually need some initial values. So what I mean by that is, for example, x0 and x1. So how do we get x0 and x1? Well, from here, from our guess. So if u0 is 2, which is equal to 1 plus 1 over 1, then x of 0 is 1. And also, since u1 is 2 plus 1 over 2, then x1 is 2. So I will just leave this on the side so we can use for further situations. Okay, so now that we have everything set up, I will plug this into here. So un plus 1 is xn plus 1, and then plus 1 over xn plus 1. Because remember, we're subbing it in with our guess. And this is equal to un, which is that. multiplied by un minus 1 squared and then minus 2, and then still make sure to minus the u1, which is 5 over 2. Okay, so now that we have this, I'm going to leave the left-hand side and work with the right-hand side. So I'm first going to leave the first term, xn plus 1 over xn. But for this, if we unpack, then we see that the middle term for this square, which is 2 times 1, which is 2, will cancel out with this. So the only terms remaining will be the first term squared plus the second term squared, and then minus 5 over 2. So now, since we want our guess to be correct, we want to match up this with some terms on the right-hand side. Well, how do we do that? Well, we have to expand this strategically. So, we want to find terms in the form of something plus 1 over that same something. Well, what terms in this are like that? Well, if we see the first term in both brackets and multiply them together, it will be xn times xn minus 1 squared. And add, if we do the last term from both brackets, multiply them together, it will be 1 over xn times xn minus 1 squared. And now we see this has the same form as this. And now, if I just expand everything else, then we will get oh my god. Then we'll get this. So now we see that this matches with this. So if we want the right-hand side to just be this, then what happens to the rest of these terms? Well, then these terms have to all equal 0. Or in other words, the first two terms are equal to 5 over 2. So if we leave this aside first and just assume that the right-hand side is just this, then we have a refined version of this. We also can see that xn plus 1 is probably this. Now, the real deal is we have to figure out what this is. Okay, so how do we prove that this is 5 over 2? So, to do that, what I'm going to do is I'm going to use this thing and plug it into this. So what I mean by that is I'm going to plug in xn is equal to, use that formula. But I'm not going to plug it in for xn minus 1, and you'll see why. So this becomes, because it's just the left-hand side. So xn is, if we use that formula, it'll become xn minus 1 times xn minus 2 squared over xn minus 1 squared plus xn minus 1 squared over xn minus 1, xn minus 2 squared. And then now we can cancel. So what we have left is, on the top, xn minus 2 squared over xn minus 1, add xn minus 1, xn minus 2 squared. Okay, so we see that the original was xn with xn minus 1. But now we have xn minus 1 and xn minus 2. So we basically reduced the foot. So if we can reduce the foot by 1 each and every time, then eventually, of course, we will reach a time where it will be x1 and x0. And that's why I told you beforehand to get our initial values ready, because then we will need it here. So this is equal to, eventually, so that's actually bad notation, dot 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 equals to x0 squared over x1 plus x1 over x0 squared, which is x0 is 1, x1 is 2, 1 squared is 1 over 2 plus 2 over 1, which is 2 plus 1 over 2, which is 5 over 2. So now we have verified that this and my guess is correct. Okay, so now we know that these two are correct. Then it's not really similar to that, right? So we want to make this even more specific. How? Well, remember when I said at the very start that there's another guess, which is xn is probably in the form of 2 to the power of something. We say an. And now that we know that this is correct, then we can plug in our xn equals 2 to the an into that and verify if this is true. So we see if we plug this in, then it becomes 2 to the an plus 1 is equal to 2 to the an multiplied by 2 to the an minus 1 bracket squared, and we can just multiply the 2, so it becomes 2 times an minus 1. So this is equal to, we can just add up the powers, so an plus 2an minus 1. So from here we get an plus 1 is equal to an plus 2an minus 1. So now this is a typical recursive equation. So what do we do from here? Well, I'm going to create a characteristic equation for this equation. So in this case, the an plus 1 will be r squared, the an will be r, and the an minus 1 will be constant 1. So we have this, which is r squared, is equal to r plus 2 times 1, which is still 2. So we have r squared minus r minus 2 is 0. And if we factorize this, then we have r minus 2 times r plus 1 is 0. So r is 2 or negative 1. So now we know that r is 2 and negative 1, and these are the solutions of our characteristic equation. Then we can actually write out how the general form of an will look like. So it will look like this. An is equal to alpha times r1 to the n plus beta times r2 to the n. So now we can plug in values of r1 and r2. So it's alpha times 2 to the n plus beta times negative 1 to the n. So now the only things that we're missing is alpha and beta. So how do we figure out alpha and beta? Well, we need initial values for an. For example, a0 and a1. So how do we figure out a0 and a1? Well, from x0 and x1. So if I write them here again, we know that x0 is 1, x1 is 2. So we know that xn is 2 to the an. So that is 2 to the a0. And this is 2 to the a1. So in this case, a0 is 0. And in this case, a1 is 1. So now we have our initial values, and we can plug it in into here, so we can have a simultaneous equation to figure out alpha and beta. Simultaneous. First one, a0. If we plug in a0 into all of this, or just plug in n equals 0, then it becomes 0 is equal to alpha times 2 to the 0, which is 1, plus beta times 1. And now, for the second initial value, we plug in n equals 1. So 1 is equal to alpha times 2 to the 1, which is 2, so 2 alpha. And then negative 1 to the power of 1 is negative 1, so it becomes minus b. So if we add them up, then we get 3 alpha is 1, so alpha is 1/3. And using equation 1, we see that beta is negative 1/3. Okay, so now we have an. I'm just going to do a little last minute change. So this is also equal to, I'm going to factor out this 1/3. So 1/3 times 2 to the n minus negative 1 to the n. So now that we know that an is this, then we see that xn is 2 to the power of this, and we see that un is 2 to the this plus 1/2 to the this. So un is 2 to the this. So I'm going to write it like that. So 2 to the n minus negative 1 to the n over 3. And then add 1/2 to the 2n minus negative 1 to the n over 3. Okay, so we want to prove that the floor function of this, or the integer part, is just this. Well, how do we do that? Well, if you remember our initial values for a0 and a1, they were both integers, right? And the equation that we used to find the characteristic equation, that was just a linear combination of the two terms before. And since the first two terms are already integers, then all other terms, of course, have to be integers. So now we know that this first term is an integer. Now we just have to prove that this bit is a decimal that's less than 1. And isn't it obvious that this is greater than 1? Because this is 2 to the power of something. Of course that's greater than 1. So if this is greater than 1, then reciprocal, it's a decimal that's less than 1. So we know that the floor of un has to be this bit, which is the integer part. So this is the final answer of this very hard IMO question. So thank you guys so much for watching, and if you enjoyed my video and you want more videos like this, please consider liking and subscribing. If you want to master something, teach it.